I'm back. Yay. Okay, all right. Okay, whatever. I think the feedback from midterm 1 is posted now. Yeah, okay, so make sure you spend some time this weekend to look at your responses from midterm 1. It should include the correct answers and your responses that you put there. So do use that feedback as preparation for, the next exam. And remember, the final exam in this course is cumulative. All right, so let's finish off chapter 4. So we are talking about reactions in water, in aqueous solution. So we just talked about a new type of unit, our concentration unit that we use to discuss, concentration of solute dissolved in solution, and that is molarity. So I told you to go to bed and say over and over that molarity, the unit is moles per liter, moles per liter, moles per liter. So that will help us in answering these kinds of questions that also have to do with concentration, where we're mixing two different solutions together and we want to figure out what is the total concentration of chloride ion that is present in this solution. So the whole idea here, we're just going off the unit of molarity. The concentration of chloride in this solution, in this mixture, is equal to the amount of moles of chloride in this solution over the total volume of the solution. So we need to think about, okay, what are the total moles of chloride present and what is the total volume within here? So this is a little bit of reading comprehension. The liters of solution, when we mix these two substances, these two mixtures together, will be 1.5 liters. All right, so do recognize that we're combining these two volumes of solution. Now the idea is, okay, we need to figure out how many moles of chloride are present total in this solution. So we need to take into account the concentration. Oh, there should be an M here. This should be 0.8 molarity HCl, sorry about that. We need to take into account the moles of chloride in both of those solutions, that both solutions have chloride present. NaCl, we have some chloride present, and HCl also has some chloride present. So how I go about this is recognize, okay, a volume times a molarity will give me my mole amount of chloride in this first solution. So I'm going to do 1 liter of that NaCl solution times its concentration, 0.5 molarity, or you can think about it moles per liter. So you see how that cancels out and gives you a mole amount of chloride. But we have to also take into account the other solution that we're mixing here. So we have half a liter of that HCl solution, so times 0.8 moles per liter. And so you can see those 2 liter units cancel out, so we get moles. And then that numerator, if we add those two values up, will give us the total amount of chloride ions in moles for both mixtures. And then if we just divide that mole amount by that 1.5 liter total volume that we're working with, this will give us the concentration of chloride total when we mix those two mixtures together. So the big idea here is I just figured out, okay, how many moles of chloride are present in both of these containers, add them up, and then divide by the total volume of solution that's present there. And so I think the answer I get is something like 0.6 molarity chloride is present once we mix these two solutions together. And to me, that number seems reasonable to me, because what I see here is that I have a 0.5 molarity chloride solution, and we have a 0.8 molarity chloride solution. So if I mix those two solutions together, the new concentration should be somewhere between there. All right, that like the concentration doesn't go up, it doesn't get like very, very diluted, it's somewhere in the middle. So to me, that value seems reasonable. All right, so using the same thought process here, we just need to figure out what is the total amount of chloride present in the two mixtures that we're mixing together here. So the only difference here is the substance. that's actually part of the solution. So the idea here is we have this, 25 or 250 milliliter 0.1 molarity magnesium chloride solution. But the problem is that we are looking for chloride minus concentration. So we'll have to do a little bit of taking care of business within this top part, our numerator part, to get moles of chloride. We can still approach moles of NaCl just the same within here. So setting this up, I'll just quickly convert this milliliter value to liters first, because I like working with liters. So I just converted that to liters. So the idea here is that the concentration of magnesium chloride is 0.1, but how does the concentration of chloride compare to the concentration of magnesium chloride? Is it just this concentration that's written right here? No, what do we have to do to that number to take into account the chloride ions, the anions that are present? We have to multiply that number by 2 because there's 2 chloride anions that are present. So I will multiply a factor of 2 and then times that 0.10 molarity number. That will give me moles of chloride, and then I can approach sodium chloride the same here. So 750 liters or milliliters, I'm sorry, times the 0.30 molarity. And because it's just a 1-to-1 ratio, we don't need to do any multiplication, multiplying by 2 to take into account the number of ions that are present. All right, and then we just divide by the total volume of solution. What's the total volume of this solution once we mix them together? Just 1 liter, yeah, so we can just divide by 1 within there. All right, and so then approaching this question the exact same, if you add those 2 mole amounts together, you get something like 0.275 molarity of chloride is present. This should probably have 2 sig figs, so we'll say 0.28 molarity of chloride. So the only difference in this second question is that we had to take into account that there's 2 chloride ions in one of those solutions. If we wanted to think about chloride ion concentration, it would be 0.20 molarity for this solution versus the actual formula unit that's given here. All right, so remember molarity, moles per liter. We're going to use that within putting everything together within solution stoichiometry. So if you drank my Kool-Aid in chapter 3 about stoichiometry and setting up our dimensional analysis, canceling out those units, what you'll see here is when we talk about molarity, moles per liter, all it is a new conversion factor that we can use in our dimensional analysis. So the idea is how we approach solution stoichiometry is the same as stoichiometry in chapter 3. We need to be working in moles. So now that we have molarity in this unit, if we know the molarity of our solution, we know the volume of our solution, now we have this new way that we can calculate moles of solute that's in our chemical reaction. So if I want to draw analogies to chapter 3, I'm doing this to show you that this isn't really a new topic. That really, this is just manipulating a unit a little bit differently. Back in chapter 3, we needed to start with the balanced chemical equation because it's the coefficients that told us, the ratio, the stoichiometry that we needed to follow. Analogous to chapter 3, when I gave you a gram amount of a substance, you knew if you use the molar mass of a substance of that particular substance, combining molar mass and a gram amount, you can get moles of that substance. So the only difference in this chapter is instead of a gram amount and a molar mass, I just give you a volume and a molarity instead. These two values together will give you moles. Just like in the last chapter, a gram amount and a molar mass gave you moles. It's just a new equality that we can play with. So this is typically how questions are worded, but I want to show a chapter 3 example to just prime ourselves how to do stoichiometry. All right, so this is a neutralization reaction where we're taking an acid and a base. and we want to neutralize it. So we want the moles of acid to be equal to moles of base. In this example, I give you mass amounts of the acid and base. So I give you the mass amount of base. I want you to calculate, tell me the mass amount of acid required. This is actually a chapter 3 question. Let's just start here as a starting place and see how molarities fit into this. All right, so you should already know how to do this. So the question here says, what is the minimum mass of HCl required to neutralize this many grams of calcium hydroxide? So we're looking for mass amounts. So I'm very nice here and give you molar masses of HCl and calcium hydroxide. I even give you the balanced chemical equation. We see that the stoichiometry here is a 1:2 ratio. And so how we approach stoichiometry in chapter 3 is we started with a gram amount, we went to a mole amount, did stoichiometry to get a new mole amount, and then used another molar mass to get a gram amount. So that's what we're doing here. You see that strategy right here. To go from the value that's given here, 1.35 grams of calcium hydroxide, how do I get to moles of calcium hydroxide? How do we do that? Go from grams to moles. Molar mass, very good. And I even give it to you. All right, then how do we go from moles of calcium hydroxide to moles of HCl? The mole ratio or stoichiometry. So in this case, is it a 1:1 ratio? No, it's a 1:2, right? You got to look at the actual number. So I call this stoich. This allows us to change from a mole amount of one substance to a mole amount of another substance. And then once we're in moles of HCl, how do we go to grams to HCl? Molar mass of HCl. Very good. Okay. So that's our strategy here. So let's put it all together. Let's start with the piece of information given here. I want to use the molar mass of calcium hydroxide. So I do 74.093 grams is 1 mole of calcium hydroxide. All right. Once I'm in moles of calcium hydroxide, I can use stoichiometry. So 1 mole of that base is 2 moles of HCl. This came from the balanced chemical formula. All right. Or sorry, the balanced chemical equation. Now I'm in moles of HCl, and now I can get to grams of HCl using the molar mass of HCl. So 1 mole of HCl is 36.46 grams of HCl. All right, this is chapter 3 stuff. This is what could have been asked on midterm 1. All right, given gram amounts, we use molar mass, we do stoichiometry here. And so I think the answer is something like 1.33 grams of HCl is required. All right. So I want us to prime ourselves of what that looks like, because the problem is that HCl, you can't actually measure the mass of it. All right, it doesn't really exist as a solid. It only exists as a liquid or solutions that we prepare in lab. So how this question is worded is not how you would actually encounter HCl. So let's change this question to, reflect solution chemistry. But I want us to think of this strategy, because what you'll see here is it doesn't change that much. All right, so here's a new question. Well, it's the same stuff. So this question is, what is the minimum volume of this concentration of HCl that's required to neutralize the same amount of calcium hydroxide? So it's the same chemical formula, the same balancing here. All right, 1 mole of calcium hydroxide, 2 moles of HCl. The only difference is that I'm not asking you for a gram amount. So if we go through this strategy, we don't want to go from moles of HCl to grams of HCl. That's not what the question's asking. It's asking, what volume of HCl do I want, given the concentration that's given in the question. So what we see here, this molarity value that's given is what's going to allow me to go from a mole amount of HCl to molarity to a volume amount of HCl. Because remember, I always like to rewrite molarities into something that's a little bit more useful to me. So if we want to rewrite that molarity as a conversion factor, 0.0723 moles of HCl equals 1 liter of that HCl solution. So this is what I mean. Once we're at moles of HCl, we can use this equality to go from moles of HCl to volume of HCl. So basically, this question starts off exactly the same. We are given gram amounts of calcium hydroxide. So we're still going to start with the molar mass of calcium hydroxide because we need to get into moles so we can use the balanced chemical equation. All right, so once I'm in moles of calcium hydroxide, I still do stoichiometry to get to moles of HCl. So 1 mole of calcium hydroxide is 2 moles of HCl. So now the difference is now we're doing a detour. Instead of using molar mass to get to grams of HCl, we're going to use molarity to get to volume of HCl instead. So do we see, if I highlight here the equality that comes from the concentration that's given here, what number am I going to put on the bottom here? The 0.07 number, because that's where the moles of HCl, that's where that unit is, all right? And then the 1 liter is going to go up top, all right? And that's basically it, all right? So again, it's the units here that help you. 0.0723 moles of HCl and 1 liter up top, and then there's your answer. It's something like you need 0.504 liters of that HCl solution, so 504 milliliters in order to neutralize it, right? That is more realistic, you know, when thinking about how you would interact with HCl in the lab. This would be more realistic. So you see, the only step that changed was that last one. Now that we're working with molarities, okay, instead of grams. Okay, so that's between a mass amount and a solution, or like a concentration. So imagine what the last one is. 2 solutions, okay? But you should know how all of this works at this point. So it's the same stuff. HCl, we want to neutralize this volume of this concentration of calcium hydroxide. It's the same strategy. It's the same strategy, except this time, instead of starting with grams of calcium hydroxide, we're starting with a volume of calcium hydroxide. So we want to actually use the molarity of that calcium hydroxide solution to get the mole amount. It's a new way to get a mole amount. All right, so if I want to rewrite that molarity of calcium hydroxide into something useful, I can rewrite it as 0.225 moles of calcium hydroxide equals 1 liter. All right, and then once I'm in moles of calcium hydroxide, I just do stoichiometry, just like always, to get to moles of HCl. I don't want to go to grams of HCl. I want to go to volume, so I use molarity again. And again, I will rewrite that molarity into a useful unit here, 0.0723 moles of HCl equals 1 liter. All right, so just how we're beginning and ending this strategy is just a little different using molarity here. So, all right, let's start off. So I'm going to start off with the volume of the base because I know its concentration. So with that volume, I can use the molarity here that I wrote, and I will put the 1 liter on the bottom, and I'm going to put the 0.225 moles of calcium hydroxide up top. All right, so now it's just a different way to get to moles of calcium hydroxide. I'm in moles of calcium hydroxide, so I can still do stoichiometry here. So I still do the 2-to-1 ratio. 1 mole of the base is 2 moles of the acid, based upon the chemical, balanced chemical formula. All right, and then the last step here is, again, use the molarity that's given here in the correct way so the units cancel. And so doing that, you'll see we'll put 0.0723 moles of HCl on the bottom and 1 liter up top. See? It's just like stoichiometry from chapter 3, no different. All right, and then that will give us our answer here. I think you need 0.934 liters. So you need nearly a whole liter of that HCl solution to neutralize that base. So like 900 milliliters, that's a lot. All right, so that's solution stoichiometry. So everything after this is basically just application of solution stoichiometry. All right, so as long as you remember concentration is the unit moles per liter, that will help you immensely here. Because there's other ways we can do calculations involving concentration. So that includes standardizing a solution. So oftentimes you will see solutions in the lab on the like the stockroom table, the solvent table, like concentrations of acid or base. The thing is that someone had to standardize it and figure out what that concentration is. You guys just write down the number that's on the label, but someone had to actually figure out what that concentration is. So this is how they do it. They use a substance called KHP, potassium hydrogen phthalate. What this substance is an acid that is, that's a solid. Because the idea here is if you can measure out the amount of solid that you use on a balance, it's going to be much, much more accurate. So we use KHP to standardize base solutions oftentimes. And this allows us to get a lot of sig figs when we figure out the molarity of that base solution. So the idea here is that you can weigh out the amount of KHP that you're going to neutralize. So in this case, this chemist weighs out 0.7, whatever grams of KHP, which we call a monoprotic acid, meaning it has one proton. And this is important because we can draw out the balanced chemical equation. If KHP is a monoprotic acid, there's just one H plus attached to that acid. All right, so I want to write that here. So HA, I'm just trying to show that that is KHP. So if HA is a monoprotic acid, how many moles of sodium hydroxide do I need to neutralize it? 1. Yes, so the ratio here is 1 to 1. Do I actually have to finish the whole reaction? No, I don't. I just need to know that this is a 1 to 1 ratio. That's important here. All right, so if you were doing this in lab, if you were actually standardizing it, what you would do is you would weigh out that KHP, you would put it in the bottom of your Erlenmeyer, all right? You would measure the starting point of your unknown concentration of base. You would mark or write down that initial volume, and then what you would do is start adding base until the first pink color persists within your KHP solution. So the idea here is the solution will turn pink the moment the solution turns basic, where it's no longer acidic. So the idea is you want to find that first instance that it turns pink. Sometimes this takes multiple trials, and that's okay. Sometimes I will do my first trial like really, really rough. I'll do it like really fast. I'll go in like 1 milliliter increments just so I can kind of figure out where the end point is. And then on my subsequent trials like 2, 3, and 4, I will basically, start my titration, go all the way to where I know the endpoint will be, and then go dropwise. So I usually always throw out my first trial within there. All right, so how do we do the calculation? What is the concentration of sodium hydroxide in molarity? So the idea here is if we want molarity of sodium hydroxide, we need to know how many moles of sodium hydroxide there are over the volume of sodium hydroxide used. So if we look through the information that's given here, it says here after 25 milliliters of base has been added is when it has been neutralized. So that 25 milliliters, that is your volume of base that is used within here, because that's how much base you used. So now the idea is, well, let's figure out how many moles of base we used. But the problem is that you didn't measure that. You measured the mass of KHP that is used. But that's okay, because if we know the mass of KHP is used, we know the molar mass of KHP. We know it's a 1-to-1 ratio. We can figure out the moles of base that were actually used. So let's actually do that. So starting with the 7.1 or 0.7137 grams of KHP, I'm going to use the molar mass that's given here. So 204.22 grams is 1 mole of that KHP, that monoprotic acid. And so that equals, where is it? Where's my answer? 0.0034947 moles of KHP. So that's how much acid you added to that solution. But the problem is that this is moles of KHP. I want moles of base. So how can I turn moles of KHP to moles of base? The chemical reaction, which we already sort of balanced here. It's a 1-to-1 ratio. So if I know how many moles of acid I put in, I know how many moles of base I need to use to neutralize it. So the idea here is that the molarity of NaOH is going to be that same number, so 0.0034947 moles of sodium hydroxide, because it's a 1-to-1 ratio, over the volume of sodium hydroxide that you use. So make sure that this is in liters, so 0.02549 liters, and then that will give you the molarity. So the idea here is you are getting the moles of sodium hydroxide from the mass in the molar mass of the acid that you used within there. All right, so I think the answer is something like 0.1371 molarity of sodium hydroxide. All right, and this will have 4 sig figs because the mass that you started with has 4 sig figs and the volume has 4 sig figs. So again, this standardization process gets you a lot of significant digits, which is good. All right, so that is standardizing a solution. So once you've standardized a solution, you can then do titrations and more, calculations involving those solutions because you have a lot of significant digits in your calculation. So here's another way to calculate concentration of a solution. So let's say you it requires this many milliliters of HCl to completely neutralize 10 milliliters of an unknown concentration of base. Right? So this is another acid-base reaction. So let's balance it. Let's make sure we balance the chemical equation. We have HCl, which is a monoprotic acid. We have sodium hydroxide. What's the ratio here? 1-to-1, yes. It's just 1 H plus and 1 hydroxide, so it's a 1-to-1 ratio. I don't need to balance the whole thing. I just need to know the ratio between acid and base here. So the same process. We want to know molarity of sodium hydroxide, so we need to figure out how many moles of sodium hydroxide were used and the volume of sodium hydroxide used. I know the denominator. All right, that denominator is that 10 milliliters that's stated in the question. That's how many, that's the volume of sodium hydroxide used. Now we just need to figure out what's the moles of sodium hydroxide. So we'll use HCl to figure that out. So the idea here is if I start with the volume of HCl, so 15.28 milliliters of that HCl solution, I'm going to quickly convert that to liters. And then what I can do is use the molarity that's given here. 1 liter is 0.2500 moles of HCl. Then I can use that 1-to-1 ratio, all right? And this will give me moles of sodium hydroxide that were neutralized in this chemical reaction, all right? So I just used the knowns from HCl. Within there. And so once you put that into your calculator, the unit of the value that comes out of here is something like, what is it? It's something like 0.00380 moles of sodium hydroxide. So the answer here when you do all of this is moles of sodium hydroxide. If we look and see how the units cancel, liters, milliliters, moles of HCl, moles of sodium hydroxide. So moles of sodium hydroxide isn't our answer. I want molarity of sodium hydroxide, so I need to divide that number by liters, the amount of solution that you actually used here, and that's 10 milliliters. So there's still one last step I need to do here. All right, moles, sodium hydroxide. All right, and then I will divide by that 10 milliliters, but make sure that this is in liters for molarity, all right? So this will give me our concentration of sodium hydroxide. And so what you get is something like 0.3820 molarity of sodium hydroxide. All right. So that is a titration between two different concentrations of solutions here, an acid and a base. So I can't ignore how high school teachers, yeah. Let me just say this slide. So I can't ignore how high school teachers taught you how to do titrations. Okay, who in here did your high school teacher teach you to do a titration using M1V1 equals M2V2? Raise your hand. Okay, so half of you. Your teacher was lazy. They were lazy and they were wrong. Okay, so a dilution, we already talked about dilutions. Dilutions, you're just adding water. Okay, that's a physical change. Okay, so when you use the dilution equation, that's just a physical change. These reactions, right, like we balanced reactions, right? These are chemical changes. So it is not correct to use the dilution equation to do these titration reactions, these titration questions, because the reasoning is that when you use the dilution equation, you ignore stoichiometry. You ignore stoichiometry. So let's try this example. So yes, if you do M1V1 on this question, you will get the right answer. But that's because the stoichiometry is a 1-to-1 ratio. That's why. That's the only reason why it works out mathematically. But let's try it in this question. So it's the same stuff where we have the same volume of acid, we titrate it completely, we neutralize an unknown concentration of calcium hydroxide. What is the concentration of calcium hydroxide in molarity? So let's balance the chemical equation. Is this a 1-to-1 ratio? No, it's not. It is a 2-to-1 ratio. We need 2 moles of HCl to neutralize it. So the idea here is if we start off, I think we'll start this off the exact same way, all right, where we will start this off the exact same way. But the idea is instead of going to moles of sodium hydroxide, we want to go to moles of calcium hydroxide. So there's a 2 moles. Oh no, sorry, it's the wrong way. There should be a 2 on the bottom. 2 moles of HCl is 1 mole of calcium hydroxide up top. And so what we get is that this solution based upon the neutralization information is 0.00191 moles of calcium hydroxide. And so if you want to get molarity, then you just divide by that 10 milliliters, but make sure it's in liters within there, all right? And so that will give you the molarity of calcium hydroxide, and it's something like 0.1910 molarity. All right, for this example, because it's not a 1-to-1 ratio, it's a 1-to-2 ratio, all right? So promise me you will not use the M1V1, M2V2 equation for titrations. Please, promise me. You pinky promise? Okay. Because if you do, this is what's going to happen. If you do use M1V1 for titrations, you're going to forget stoichiometry. You're going to forget. And you know for a fact on exams, we are never going to give you a 1-to-1 ratio. It's never going to be 1-to-1. We're going to make it harder. No. All right? Because we want to trick the students who think, oh, I can just use M1V1 and I'll get the right answer. okay? This happens every year. Students are like, I learned this in high school, I'm gonna do it this way. But then I get emails from students saying like, I was doing homework, I was doing a titration, and I did M1V1 and I got the right answer. But then on the next question, I didn't get the right answer. But then I multiplied my answer by 2, and then I was right. And then they were confused, like why multiplying their answer by 2 got them the right answer. I'm like, you are ignoring stoichiometry. Just forget what you learned in high school. Because honestly, your teachers were just lazy. They were lazy. They'd rather just teach you the trick instead of teaching you, hey, this is application of stoichiometry. A chemical reaction is happening. All right, so again, promise me you won't use M1V1. You won't use it. Okay, very good. All right, so I'll get off my soapbox now. All right. So a couple more examples here, applications of solution stoichiometry. We can also calculate the molar mass of an unknown acid or base. Same idea here, using concentrations and masses of known solutions here. So we want to know, we are titrating an unknown monoprotic acid with a certain volume of standardized sodium hydroxide with that concentration. So here I'll just highlight those, the sodium hydroxide. What is the molar mass of the unknown monoprotic acid? So the idea here is this question's asking for molar mass of the acid. So molar mass is equal to the gram amount of the acid divided by the moles of acid that's present. So if we think about this, the pieces of information that are given here, I already know the numerator, right? The question tells me the gram amount of the acid that's present. I just need to figure out the mole amount of acid that's present. So we're going to approach this the exact same way we did those titration problems. We'll use the standardized solution to figure out the moles of base present, and we can relate that to moles of acid present. The only thing that's missing here is the stoichiometry. If this is a monoprotic acid, what's the ratio? 1 to 1, yes, it's just 1 to 1 simply. All right, so the idea here is if we take that volume of base, I'm just gonna convert that into liters right now, so 0.02133 liters of that sodium hydroxide. Next, I use the molarity, so 1 liter is 0.1898 moles of sodium hydroxide. But the thing is in my equation, I want moles of acid. So I want to do stoichiometry to get moles of acid, but it's simply a 1 to 1 ratio. So 1 mole of base is 1 mole of acid, HA. All right, and so this will tell me how much acid I have in moles in my Erlenmeyer here. So it's 0.00484 moles of HA is present in that container. And so that will be my denominator for this equation up here. Molar mass of HA is the gram amount of HA, which was given in the question, so 0.4937 grams over the mole amount, so 0.00484. This should have 4 sig figs. Moles, and so that will give you the unit of grams per mole. And so the molar mass here is something like 121.9 grams per mole. All right. So you see that the work we do, liters, use molarity, get moles. We've been doing that in all of these different application-based questions. We're just using the moles of substance we get out of it a little bit differently, either in a titration question to get concentration or to get molar mass in this question. So let's do one more here, application of solution stoichiometry. Again, it's a molar mass one, but the difference is it's the same exact information. The only thing I changed is instead of we're neutralizing a monoprotic acid, instead let's neutralize a diprotic acid instead. So the idea here is it's the same numbers here. We have an unknown diprotic acid that we neutralize with sodium hydroxide. What's the molar mass? So the idea here is I have the half neutralization reaction over here. Is this a 1-to-1 ratio? No, it's not. It's going to be a 1-to-2 ratio. I need 2 equivalences of base in order to neutralize it. So the work is the exact same as before. We already know the numerator, all right, the gram amount. We just need to figure out, okay, how many moles of acid are present. So it's actually the exact same setup as the previous question. It's the same amount of base, the same concentration. The only difference is that we need 2 moles of sodium hydroxide to neutralize 1 mole of your acid. That's the only difference. So you'll see that the mole amount of acid is half of that than the previous question. So I think the amount is 0.002024 moles of H2A. All right, and so then to get the molar mass, you will just take the mass that's given in the question, so 0.4937 grams, and divide by that mole amount that we just got. And so that's it. The only difference in this example is the stoichiometry. All right, so do not forget the stoichiometry. And so you see that the molar mass of this acid, this diprotic acid, is something like 243.9 grams per mole. Don't forget the stoichiometry. Okay, very good. All right, so now let's put it all together within solution stoichiometry and apply the idea of limiting reactants also. All right, so in this example, I give you a volume and concentration of 2 of the reactants, and I just say, okay, what mass of product do you make? So the idea is the exact same. We just do solution stoichiometry, but this time we do it twice because we need to figure out what is the limiting reactant. So in this example, we're combining barium chloride and sodium nitrate, and I'm asking what is the theoretical yield. The problem is that the chemical equation I give you doesn't have states, so we need to figure out which substance is the solid. All right, because that's what we're trying to figure out. What is the theoretical yield of the solid that is produced in this precipitation reaction? So how do we figure out the states of the products? Is this something we need to remember? No. You just use what? The solubility table. But looking at this, do you know which one the solid is? Yeah, because sodium chloride is aqueous. All right, you know that that's aqueous, that it like will dissolve in water. Your observations tell you that. And so that means that barium sulfate will be the solid. Yeah, but the table says it too. Barium is one of the exceptions under sulfate. All right, so the idea here is that we have volume and concentration of 2 of the reactants. All right, we want to figure out what is the theoretical yield. So my strategy is I want to start with each reactant and figure out how much product does that make, and then you choose the smaller one. That's it, just like we did before. So I'm going to start with 1 liter of that barium chloride solution. All right, so basically I'm figuring out, okay, if all of that barium chloride reacts to make barium sulfate, how much do I make? So 1 liter of barium chloride, the concentration here is half molarity, so 1 liter is 0.5 moles of barium chloride. And then I see it's just a nice 1-to-1 ratio. 1 mole of barium chloride is 1 mole of barium sulfate, which is our solid that we're focusing on here. And so then I can use the molar mass of barium sulfate that's given. 1 mole of barium sulfate, SO4, is 233.38 grams, all right, equals something. Then I do the same thing with the other reactant. So this time it's 1 liter of sodium sulfate, SO4, sodium sulfate, and use the molarity. So 1 liter is 1 mole of sodium sulfate. I think it's a 1-to-1 ratio again for sodium sulfate to barium sulfate. And then I use the molar mass of barium sulfate to get a gram amount. And so what we see here, the limiting reactant is going to be the barium chloride. This one is limiting because when you calculate these amounts, you get that barium chloride will make 117 grams of product, and sodium sulfate will make 223 grams of product. So it's that 117. I think this should have 2 sig figs though, so 120 grams of product is what's made here. So same idea here with limiting reactants that we did in chapter 3. You just have to do the calculation twice to figure out which one's actually limiting you. And so in this case, sodium sulfate is actually in excess. All right. So the last slide here is the same question, but we're going to address everyone's favorite, and that's BCA tables. All right. So it's the same exact question. This chemist, we're mixing 1 liter of half molarity barium chloride, 1 liter of 1 molarity sodium sulfate to give a total volume of 2 liters. And now the question is, what's the concentration of everything after the reaction is done? Yes. So this question, it's very comprehensive. It's very comprehensive. So often, like, there's no getting around a BCA table, all right? It's just better to look at everything holistically using a BCA table to see, okay, what's left over, what's completely consumed within here. So I already have the BCA table kind of filled out for you already, where I took the liter and mole amounts, or liter and concentration amounts of the 2 reactants, all right? And I put the mole amounts into the BCA table. So just looking at this, the mole amounts here, can you clearly see which reactant is the limiting reactant, right? It's the barium chloride. There's less of it, and everything's a 1-to-1 ratio, so it's nice. That barium chloride is the limiting reactant. So the limiting reactant, what's special about that in a BCA table? It gets consumed, completely consumed. So after, there should be 0. So that means the change line for barium chloride should be negative 0.5 moles. So that means we can fill out the change line for everything else. So if I consume half a mole of barium chloride, how many moles of sodium sulfate do I also consume? Half a mole. So minus 0.5. How many grams of barium sulfate do I make? Half a mole, but this time it's plus half. Then how many moles of sodium chloride do I make? 1, because there's a 2 coefficient here. So this is plus 1 mole. And so then when we add everything, we see that afterwards there's 0 moles of barium chloride left. There's 0.5 moles of sodium sulfate. There's half a mole of barium sulfate, but this is a solid. Note that that's a solid. And then there's 1 mole of sodium chloride. All right, and the idea here is that all of this is in 2 liters of solution because we mixed 1 liter each, all right? All of that's in 2 liters of solution. So we should be able to go through here and determine what is the concentration of all of the ions that are present. All right, so we'll do the first one. We'll do barium 2+. Look and see in the afterline, where is all the barium in the afterline? Where is it? It's in barium sulfate. So is it in the solution? Where is the barium? It's in a solid. It's not dissolved. So barium, the concentration of barium 2+ is actually 0 because all of it's in the solid, right? If it's in the solid, it's not floating around in the solution. Okay, let's move on to the next one. Let's look at concentration of sulfate this time, SO4 2-. All right, look and see in the afterline what substance contains sulfate. Sodium sulfate. So again, sulfate in barium sulfate doesn't count because it's a solid and it's like stuck at the bottom. We're looking at concentration of stuff that's in the actual water. So the idea here is that the sulfate concentration is coming from sodium sulfate. So my idea here is there's half a mole of sulfate that's present in 2 liters of solution. So the concentration is 0.25 molarity. of sulfate. You following me? Good? Okay. What should we do next? Let's do sodium. We'll do sodium. Okay. So ask yourself, in the after line, what substances contain sodium? The only thing is sodium sulfate. All right, so if there is half a mole of sodium sulfate, how many moles of sodium are there? 1. Yes, because there's 2 sodiums for every 1 sodium sulfate. So the idea here, it's actually 2 times 0.5 moles over 2 liters. So the concentration of sodium, oh wait, that's not all the sodium, crap. Okay, crap. All right, so yes, you're right. There's 1 mole of sodium that's coming from sodium sulfate, but what did I forget? There's more sodium present floating around, and it's coming from sodium chloride. So it's 2 times that half mole that's coming from sodium sulfate, and then 1 mole that's coming from that sodium chloride. All right, that's also floating around. And so then divided by 2 liters. And then that gives you, what's the answer there? 1? Is it 1 molarity? Okay. All right. Is it 1? Okay, good. All right, and then the last one here is chloride. And so the only source of chloride is coming from sodium chloride. So 1 mole over 2 liters is 0.5 molarity. Okay. That is literally everything. Stoichiometry, limiting reactants, BCA tables. I don't think it gets any harder than like this question right here. I even tried to use really, really easy numbers to simplify it here, but yeah, that's everything. That's everything with solution stoichiometry. Okay. All right, so we have 4 minutes. So I'm gonna start chapter 5, but just the flavor of it, all right? I'm just gonna start the flavor of it because I wanna blow something up. Yeah? So chapter 5, we're taking a big step in a different direction, all right? Okay, yeah, so chapter 4 is done, so that means chapter 4 homework is due Sunday. Okay, great. So we're moving on to energy. So the idea in chapter 5 is that, well, in chapter 3 and 4, we talked about, balancing chemical reactions. We just focused on actually balancing the atoms. The atoms, right? Like, number of atoms on each side are the same, make a match. So a detail that we've kind of ignored is the idea that energy is also involved in chemical reactions. Kind of like redox reactions, how like behind the scenes electrons are being transferred, but behind the scenes energy is being transferred in chemical reactions also. So this chapter is hard. Actually, if you surveyed 1210 students, I think the majority of them would say this chapter is the hardest. And you know why? It's because if, like, you're good at math, right? Like, you can add the numbers, you can crunch them. But the problem is like, you can be really good at the math, but where you'll mess up is the sign. Like, whether it's a positive or a negative sign, okay? That's where you screw up. And I know why you screw up. It's because as humans, we are really selfish. So we think the world revolves around us. The majority of us think that we are the system, okay? And that'll make sense soon. It'll make sense soon. But the problem is in chemistry, you are not the system. The chemical reaction is the system. You are actually the surroundings. What you observe are changes to the surroundings. And you need to get that into your head right now. And so, because you'll oftentimes, like, you'll go through all this work with all the math and whatever, and at the end, you'll just be off by a sign, like a plus or minus sign. And I don't want you to go through, all that heartache. Just remember, you are the system. The chemical reaction is the surroundings, all right? So, what? What did I say? You are the surroundings. I'm sorry. Yes, you are the surrounding. The chemical reaction is the system. So we are doing a lot of the ideas of chemical energy is based upon the first law of thermodynamics. I like this cute little meme. All right. We are studying the first law of thermodynamics in this course. you have to wait until 1220 to learn about entropy, the chaotic cousin of the first law of thermodynamics, all right? So I wanted to remind you, all right, you are the surroundings, okay? So the idea here is we've seen this reaction before, right? Okay, so let's blow something up. So you tell me, where is energy going? In this reaction, remember, the balloon is the system. You are the surroundings. So everyone do the ear thing, okay? Yes, the ear thing. Yes, everyone has to do it. Everyone has to do it. Everyone's got to do it. Okay. So think about where energy is going. Okay. So, like I said, we are very selfish. Doesn't that just seem like a positive sign? Like that seems like a positive number, like whatever happened right there. That was a positive amount of energy. But the thing is, you are the surroundings. So if you saw an increase of energy coming off of the reaction, that means the reaction must have lost that energy. So this chemical reaction has actually a negative sign attached to it. Even though when we saw it, it seems like a positive number, all right? But don't be selfish, okay? You are the surroundings, the chemical reactions, the system. All right. Have a good weekend, everybody. Yes.